Okay, so in this one we have a finite group G. We have to prove that there exists a positive integer n such that the nth power of any element in G equals the identity. Note that n is independent of A, of course. To solve this one, we first show that every element in G has a finite order, is of finite order. So let A belonging to G be any element. Consider the elements A, A square, A cube, and so on. All the positive integral powers of A. They all belong to G because G is closed. Since G is finite, not the above list, the elements in the above list, that is this one, cannot all be distinct. Because if all of them are distinct, then there are infinitely many elements in this list, which coupled with the fact that all of them are in G would make G infinite. So finiteness of G is violated. So they cannot be all distinct. Thus, there exist positive integers I and j such that I is less than j and a to the power I is equal to a to the power j. There will be many repetitions like this in this list. We need only one. Then a to the power j minus I is the identity. Now note that because of this inequality, j minus I is a positive integer, is itself a positive integer. And so there is a positive integer such that the corresponding power of A equals the identity. That means there will be one such least positive integer for which also this equation is true, and that just tells us that the order of A is finite. Since this is a positive integer, this is finite. So we have thus shown that every element in G has finite order. Now since G is finite, its elements can be listed. and let these be the elements. Where m is some positive integer. M is the order of G. Consider the positive integer n, which is the product of the orders of all the elements in G. Since all the elements have finite orders, so these factors, each one of them is a positive integer. So their product is also a positive integer. For any integer k lying between 1 and m, we have ak to the power n. Okay, so ak is any element in G, so we are calculating the nth power of ak. Now by one of the rules of exponents, this order of ak will appear somewhere in this product. So by that rule of exponent, you know which one of the two, this can be written as ak plus 1 am. Okay, now this one, because this is nothing but the order of ak, so this power of ak is equal to the identity. So this is equal to the identity. That means the nth power of every element of G equals the identity, and this n clearly does not depend on the elements themselves. Note one more thing, that in place of this n we can take any positive integral multiple of n. So n is not unique. However, it does not depend on the elements. It depends on the elements in this sense, but it does not change with the elements. The choice of n remains fixed as we change the elements. So this completes the solution. Next, exercise 32. Determine the subgroup lattice for Z12 or Z12. Okay. Now we know that, of course, we know what subgroup lattice is. The subgroup lattice of a group shows all of its subgroups and how each one is contained in another one, or if they are not contained. That relationship is shown at once by the subgroup lattice. It's a picture, it's a diagram which is a pictorial representation of that relation. So now, since we know that this group is a cyclic group, so by the fundamental theorem of cyclic groups, all the subgroups themselves are cyclic and we know how to find them. You just have to look at all the positive divisors of 12. So these are the subgroups. These cyclic subgroups are all the subgroups of C12. And the one generated by 12, of course, is the trivial group consisting of only the identity element. Okay. Now the relationship among these subgroups, that is which one is contained in which one, that is shown by the subgroup lattice like this. Without writing, you can write one line here. The subgroup lattice for C12 is as follows. I am not writing that. So the largest one is this, which is the group itself. And then we have the cyclic subgroups generated by 2 and 3. And then the ones generated by 4 and 6. And lastly, the trivial group. So now, because these two are subgroups of this, so we join them. It's not necessary you have to join them by a straight line. You can join them in any way you want, by some curved line or in some other way. The only thing is that the subgroups which are related, there should be a link between them. So in that sense, this is actually going to be a graph. Then this is a subgroup of this. Okay, like that, this is also a subgroup of this. At the same time, this is a subgroup of this. And the trivial group, of course, it's a subgroup of everything. So they join like this. Okay. Note that this is not a subgroup of this, so we haven't joined them by some edge. So this is the subgroup lattice for Z12. Lattice is a technical term which means a set with a partial order on it, that is a partially ordered set. The difference between the partial order in this case is set inclusion. Of course, we are not, you can say that, okay, 0, since 0 is, this subgroup is a subgroup of every group. So not just these two edges, we should have drawn these two edges also, these three edges also, but that's not how the subgroup lattice is drawn. It shows all the relations, but not by joining all the edges that can be joined. If you just think of this relation, automatically, because the relation is transitive, any partial order is a transitive relation. So since this is a subgroup of this and this is a subgroup of this, automatically from that itself we know that this is a subgroup of this. Okay. So in that sense, this representation is minimal. We are not joining everything that can be that can be joined. So this is the subgroup lattice. Then The next one is just like this, but that is a more general one. Exercise 33. Determine the subgroup lattice for this group, where P and Q are distinct primes. You can see that it's a more general version. It's a generalization of this one, because 12 is 2 square times 3, where 2 and 3 are distinct primes. So here also we can write the solution correspondingly and similarly. Just like 12, the positive divisors of p square q are 1, p, q, p square, pq and p square q. So 1, p, q, p square, pq, and the one generated by p square q, of course, is the trivial one, also generated by 0. So it's similar. So like that. Then another one on subgroup lattice. Determine the subgroup lattice for 8. The difference between 12 and 8, other than the fact that they are different numbers, is that 12 has two distinct prime factors, 2 and 3, whereas 8 has only one prime factor, 2. So its positive divisors are all powers of 2, that is 1, 2, 4 and 8. So accordingly there will be 4 subgroups. So in that sense, its subgroup lattice will be somewhat linear. In the terminology of graph theory, it will be a path, and it will be this path. Where we join the things like this. Okay, because of lack of space, I'm not able to show it properly, but you can see that it goes vertically downward like this. And just like this to previous exercises, this one also has a general version. determine the subgroup lattice for set p to the power n, where, so just like 8, this also is a power of a single prime, like 8 is a power of 2, where p is a prime and n is a positive integer. In this case, the lattice is this. That this is the path. Exercise 36. Prove that a finite group is the union of proper subgroups if and only if the group is not cyclic. Okay. So we start by considering a group, let G be a finite group. First, we assume that G is cyclic. So that G is generated by one of its elements for some G belonging to G. Now we are supposed to show that expressibility as a union of proper subgroups implies that the group is not cyclic, and conversely also, if the group is not cyclic, then it can be expressed as a union of proper subgroups. Now here we have assumed that the group is cyclic. That means we have to show that it cannot be written as a union of proper subgroups. Contrary to that, we suppose that it can be written in such a way. Suppose G is the union of proper subgroups Okay, then what is the implication of this supposition? Since small g belongs to G, small g being a generator of capital G, so it itself will belong to G. So small g will belong to that union of some proper subgroups. Small g, so that means what? Small g will belong to some proper subgroup. Belongs to some proper subgroup H of G. Okay. But then all integral powers of G will also belong to H, because H being a subgroup is closed. Integral powers of G will also belong to H. Which implies but all the integral powers of small g constitute the entire group G. So this is contained in H. But this contradicts the fact that H is a proper subgroup of G, because since H is a proper subgroup of G, so there should be at least one element in capital G which is not in H. This inclusion, however, contradicts that. So that's why our supposition is wrong. Thus our supposition is wrong. That is, G is not the union of proper subgroups. Okay, so what have we shown here? We have shown that if G is cyclic, then it is not the union of proper subgroups. What is the contrapositive of this statement? If G is the union of proper subgroups, then it is not cyclic. So equivalently we have shown that also, because any statement, I mean any implication and its contrapositive are logically equivalent. In other words, if G is the union of proper subgroups, then we have, or we can just directly write, then G is not cyclic. Okay, Now we have to prove the converse, namely if G is not cyclic, then it can be written as a union of proper subgroups. So conversely, so that was our first assumption that G is cyclic. So conversely, assume that G is not cyclic. I am not sure how the finiteness of the group is being used, because I don't see any use of finiteness. The same solution, according to me, will also work in any group, not necessarily a finite group. If I am missing something, please let me know. Okay. In this part, in one half of this solution, I don't see any problem. Now we are going to see the converse. Conversely, we have assumed that G is not cyclic. We now have to show that G can be expressed as a union of its proper subgroups. Now G is equal to the union of all cyclic groups generated by the elements of G. Do you see how this equation is true? First of all, for any element G belonging to G, the cyclic subgroup generated by small g is of course contained in G. So the union of all such cyclic subgroups is contained in G. The right hand side is a subset of G. That is trivially true. Conversely, if you take any element in G, then that element belongs to the cyclic subgroup generated by itself. So that element will belong to this union. So G is also contained in this union, and that's why these two are equal. Okay. Since G is not cyclic, this is a proper subgroup of G for every G belonging to G. Because if one of these cyclic subgroups becomes equal to G, then G is cyclic, which contradicts our hypothesis that it is not cyclic. So that means this is a union of G as a union of proper subgroups. That's what we wanted to show. So that is the converse part, and the solution is over. Next, show that the group of positive rational numbers under multiplication is not cyclic. Okay. So this one also will be solved by contradiction. Suppose that the mentioned group is cyclic. Keep in mind we are having the set is the set of positive rational numbers. Then there exists a rational number x, or in fact since we are considering rational number, let us denote it by r, greater than 1 such that the set of rational numbers is generated by r, and this consists of all the integral powers of r, because that is the definition of a cyclic group. Minus 1, r to the power 0, which is 1, then r square, etc. Okay, since r is greater than 1, we have not only can we list the elements of Q like this because of our supposition, but because of this condition, this is the natural order of these rational numbers. That is, we have this is less than r to the power minus 2, which is less than r to the power minus 1, which in turn is less than 1, and so on. Okay, now consider the rational number t, which is the arithmetic mean of 1 and r, 1 plus r divided by 2, or simply what we call the average of 1 and r. There is no doubt that this is a rational number because we have added two rational numbers 1 and r, and we have divided that sum by 2, so this is a rational number. And we know one more thing, this is the mid on the number line, this is the midpoint of 1 and r. The thing we need from this is that it strictly lies between 1 and r. Since is less than r, we see that that is t does not belong to the cyclic group generated by R. Why? Because T is greater than all these elements and T is less than all of the other elements. So clearly T is not equal to any integral power of R because of this order relations. So and that means T does not belong to this cyclic subgroup, but T is a rational number, so that is a contradiction. This is a contradiction and hence our supposition is wrong. That means the positive rational numbers, the multiplicative group of positive rational numbers cannot be a cyclic group. So there the solution ends. Then next, (38). Consider the set show that this set is a group under multiplication modulo 20. By constructing its Cayley table. Okay. What is the identity element? Is the group cyclic? And one more thing, if so, find all its generators. Okay, so let us create the Cayley table. There are 4 elements. So in the Cayley table, we will have 5 rows and 5 columns. 4, 8, 12, 16. 4, 8, 12, 16. The operation is multiplication modulo 20. That means we have to multiply two elements and then we have to divide the product by 20. The remainder is the result. Remainder is the product of the two elements under this operation. So you can calculate and you will see that you get these things. 16, 12, 8, 4, then 4, 16, 8, 4, 12 and 16. Because the operation is commutative, so the other half, the lower diagonal half of the Cayley table can be found from this one itself. That is, this will be the first, you make the first row the first column, 8, 4, you make the second row the second column, 16, 8, and you make the third row the third column. We already have 8, 16, 4, like 8, 16, 4, and we need 12. Okay, so this is the Cayley table. Now multiplication modulo 20. Okay, so from the Cayley table we immediately see that the given set is closed, and multiplication modulo 20 is an associative operation that is also known. So we have closure property, we have associativity. Now it has been specifically asked, we have to ascertain the identity element, and that identity element, if you look carefully, is 16, because 16 times 4 is 4, 16 times 8 is 8, 16 times 12 is 12, and 16 times 16 is 16. And similarly, 4 times 16 is 4, 8 times 16 is 8, 12 and 16. So 16 is the identity element. Just like that, you can find inverses also. The inverse of 4 is 4 itself, because 4 times 4 is the identity, 16. The inverse of 8 is 12, because 8 times 12 is 16, and also 16 times 12, 12 times 8 is 16. So this is the inverse of itself. These two are pairs of element and its inverse, and 16 of course is its own inverse, because 16 is the identity element. From the Cayley table above, we see that our set is closed under multiplication modulo 20. Okay, then multiplication mod 20 is known to be an associative operation. So that part is over. The element 16 is the identity element. The inverses of 4 and 16 are 4 and 16 themselves. The inverse of 8 is 12 and the inverse of 12 is 8. Okay, so we have said what the identity element is, and we have also shown that this is a group. Thus, this is a group under multiplication modulo 20. Oh, is it 20? Am I writing correctly? Yes, modulo 20. Let's just keep the table for, as long as we are writing the solution. Modulo 20. Okay, next we have to see whether the group is a cyclic group. Note that eight square is what? 8 times 8, 4. What is 8 cube? 8 cube is 8 square times 8. Which is 4 times 8. 4 times 8 is 12. And 8 to the power 4 of course will be, no, we cannot say that, no, because we don't have Lagrange's theorem yet. Anyway, we can calculate it from here. By the rules of exponent, we have this. So this is 4 square, that is 16. So the fourth power of 8 equals the identity, and no lower positive integral power of 8 equals the identity, because 8 itself is not equal to the identity. So that means 8 to the power 1 is not identity. 8 square is not identity. 8 cube is not identity. Only 8 to the power 4 is the identity. Thus, the order of 8 is 4. So that means the cyclic subgroup generated by 8 will have 4 elements, and since the original set itself has 4 elements, so the group is generated by 8. It is a cyclic group. That is, the group is a cyclic group. Okay, now since 16 is the identity element and the group has 4 elements, so 16 itself cannot be a generator. 8 is a generator, we have already seen that. 4 cannot be a generator because 4 square is 16 and 4 itself is not the identity. So that means the order of 4 is 2, it's not 4. So 4 cannot be a generator. Now what about 12? Since for 12 also you will see that the order is just like 8, it is 4, so it is also a generator. So let us see that 12 square is 4. 12 cube is 4 times 12, which is 8, and 12 to the power 4 is 16. So 12 is another generator. Okay, so that completes the solution. We will solve 2 more because we have to reach exercise 40. Give an example of a group which has exactly 6 subgroups. Including the trivial subgroup and the group itself. And then generalize to exactly n subgroups. For any positive integer n. Since so far we know, so far means yes, we in a general finite group also we can say a lot about the subgroups that it will have. Not all subgroups, but some special types of subgroups. We will see that when we come across something known as Stiller's theorem for finite groups. But so far we have seen we have determined all the subgroups of a cyclic group. So naturally our example will be a cyclic group, and we have already come across the, for example, when we determine the subgroup lattice for a group, there we have seen that the subgroups of this are that is one more than this exponent. So we can use this observation, and in fact we have seen the general case also, zp to the power n. So we can use this observation to have our example here. The group, we need exactly 6. So that means this has exactly if you want, you can change this prime also. Nothing will, I mean the number of subgroups will not change. The group and its subgroups will themselves change, but the number will remain the same. It depends only on this exponent. For, and the other part, for any positive integer in the group n minus 1 has exactly n subgroups. So that is the solution. Okay, and then finally exercise 40, let m and n be elements of the group, the additive group of integers. So that means m and n are integers. Keep in mind, m and n may be negative also, or one of them may be negative. Anything can happen. Just we are given that they are integers. Find a generator for the group, the intersection of the cyclic subgroups generated by m and n. We know that the intersection of any two subgroups is itself a subgroup, so that means this is a subgroup of Z. But at the same time we also know that this is a cyclic group. So by the theorem of fundamental theorem of cyclic groups, this itself should be a cyclic group. So it will have its own generator. So we have to find one such generator. if at least one of these integers is 0, if this is equal to 0 or n is equal to 0, then one of these cyclic subgroups, at least one of them will be the trivial group. So the intersection itself will be the trivial group. Then or and hence in this case we have so this is a simple case where 0 is the generator. So now we can assume the case where none of these integers is 0. Then the absolute values of these integers are positive integers. And the cyclic subgroup generated by M is the same as the one generated by the absolute value of M. Similarly, we have this. Okay. Now we claim that this equals the cyclic subgroup generated by the LCM of this and this. We now show that this intersection, which is nothing but the original intersection, is equal to the cyclic subgroup generated by the least common multiple of these positive integers. Because we are dealing with positive integers, so least common multiple exists. Let k be any element in this intersection. Then k is a multiple of both and this, that is this positive integer divides k and this positive integer also divides k. So k is a common multiple of this and this. So k will be divisible by their least common multiple. That is one of the properties of the LCM. Then divides K, that is K belongs to the cyclic subgroup generated by the LCM. So any element in this intersection is here. Is contained in this one. Next, let L be any element here then LCM divides L. But LCM of these two integers is, by the very definition of LCM, divisible by both the integers. Since this divides, because LCM being the least common multiple is after all a common multiple. And we have this. Hence, L is a common multiple of mod M, and it's also a common multiple of mod N. So it will belong to the corresponding cyclic groups, that is L belongs to their intersection. This implies that this is contained in the intersection. So we can now combine these two inclusions, this one and that one. Or in fact, let us write like this, since we were originally trying to find this I almost forgot about it. So in case at least one of these integers m or n is 0, then this intersection is the cyclic subgroup generated by 0. But if both of them are non-zero, then LCM of these two numbers is a generator. Okay, in both the cases the intersection is a cyclic group, just like every subgroup of Z or Z is a cyclic group, so this one is also a cyclic group, and these are the two generators in the two cases. So that completes the solution. So we end the video here. in the next one we will solve 10 more exercises. There are many, but we have to move steadily. We cannot rush through the things. Anyway, so if you want to comment on these things, you are free to comment in the comment section, or you can mail me also in the usual address. So with that, I sign off for tonight. So until the next one, this is me, Lucifer, from a mathematical room. Have a nice night.